So welcome to part 4 of the lectures on the P-block elements and their compounds, and this will be the last video for the lecture 6 part of the talks. And in this video, we're going to be looking at the group 15 elements. Group 15 is known as the nitrogen family, and it contains nitrogen, phosphorus, arsenic, antimony, and bismuth. And again, this time, like we've seen in the last few groups, they're really different to each other, physically and chemically. So nitrogen is a non-metal and a gas. Phosphorus is a non-metal and a solid. Antimony and arsenic are both semi-metal solids, so I guess they're similar to each other. And bismuth is a metal. And that bismuth, it looks really cool as a solid. So if you can find crystals of bismuth, they just look really nice looking metal. Now with this far over the P block, all the compounds are covalently bonded. And the most common oxidation states are +3 and +5. Now this is the last group where the inert pair effect has an effect. The inert pair effect happens. So +3 is more common at the bottom because of this, and +5 is more common at the top. But there's a really wide range of oxidation states as possible in group 15, from -3 to +5. And we'll see with nitrogen over the next few slides that has loads of different oxidation states. So we'll start off by looking at nitrogen and just a few facts about itself. So it occurs naturally as a gas, we said N2, and this is the main component of the atmosphere. It's almost 80%. It's an essential component of proteins and is in all living organisms. And nitrogen from the air is used to produce the second most widely produced chemical, ammonia, which we talked about a lot in the hydrogen lectures and how important that is. Now N2 itself is pretty unreactive. It's got a really strong triple bond, so it's nearly 1,000 kilojoules per mole. So it's a very strong bond, but it's not impossible to break. One reaction that actually does occur and has a big effect on the world is with oxygen. So in car engines, especially diesel engines, where there's a big excess of oxygen, NO gets formed through the high temperatures and nitrogen and oxygen both being present. And this is a greenhouse gas. It's also quite weird in that it can form both anions and cations with itself. So you can get N5 plus, which is shown here, or N3 minus, which is shown here. I've already said that nitrogen can form lots of different oxidation states. And if we look at the oxides, we can see that it can have 5 different oxidation states. Now there are lots of different nitrogen oxides. This is unique to nitrogen. None of the other group 15 elements do this. And they all contain a series of multiple bonds between nitrogen and itself or oxygen. So we've got examples here. N2O, which is laughing gas, is in the +1 oxidation state. NO is in the +2. NO2, which is also from car exhausts, is in +4. You can get +5 for this dinitrogen pentoxide. So NO and NO2, as I was saying, are both formed formed in engines and contribute to car emissions, and they're collectively called NOx. And as all of these can, they react with moisture, such as clouds, to form nitric acid, and that's where acid rain comes from. Nitrogen is also commonly found in explosives. So nitrogen oxide containing compound is nitroglycerine. So if you take off these nitrate groups and just have hydrogens here, it's glycerol. But then we replace the hydrogens with nitrate groups, and you get nitroglycerin, which is very explosive. Moving on to the halides of nitrogen, one of the really interesting bits of chemistry of these is how they become a lot less stable going down the group. So NF3 is colourless, it's a thermodynamically stable gas with a trigonal pyramidal shape. This is shown here, and this is the same shape as ammonia would have. And this is very stable, doesn't react with water, acids, alkalis. It's just happy to exist. But then moving down the group, they turn from gas to liquid and they become much more reactive. So NCl3 is an explosive liquid that will react very rapidly with water. And then going further down, they become solid and more reactive to the extreme of nitrogen triiodide. Now, when this is dried, it's a shock or touch explosive, and it's very sensitive. The YouTube link down here is an example of someone with a feather duster creating an explosion by touching it. And you'll see at the end there's a big purple cloud as well, and that's because the explosion gives off iodine, which is purple coloured. Moving down group 15, we get to phosphorus, which is really interesting and really explosive, even in its elemental form. So it exists in 3 allotropic forms, which are referred to as white phosphorus, red phosphorus, and black phosphorus because of their colour. And these have different connectivities. So white phosphorus have just discrete P4 tetrahedra. Then red phosphorus are P4 units linked into chains, and these are planar. And then black phosphorus, the connectivities, really big. These are actually P6 cyclic compounds formed into layers. So the chair conformer as well. This is something I don't know if you will have seen it before or will see it in the future organic lectures. It's very similar to cyclohexane. So it's why you might not be able to see that they're cycles. The chair conformer is like this. And then there's 6. So you've got 1, 2, 3, 4, 5, 6. 6 atoms in a hexagon, but it's not a planar one. And these P6 cycles make a layered structure in black phosphorus. And as the connectivity goes up, the reactivity goes down. So white phosphorus has to be stored underwater as it ignites spontaneously in air. And this YouTube video here shows what happens when you add a little bit of oxygen to a fair bit actually in the video of white phosphorus. This is very reactive. White phosphorus is also used in matches, and this YouTube link actually shows how what components are in matches and how matches work with the phosphorus. And if you heat the white phosphorus to 300 C, and obviously not in the presence of air, you get red phosphorus. And then heating it even further gives you black phosphorus. And as I say, as the connectivity increases, the reactivity decreases. So black phosphorus is a lot more stable. And it's mainly used to produce phosphoric acid, which is found in large quantities, in fact, in Coca-Cola. And let's wrap up by looking at the oxides and halides of phosphorus. So the phosphorus oxides are nowhere near as numerous as the nitrogen ones. And there are just 2 oxidation states of phosphorus here. So we've got P4O6, where phosphorus is in the +3 oxidation state. And this is formed when you burn phosphorus, or phosphorus burns itself, in air. But there's a limited supply of oxygen. If there's an excess of oxygen, you get P4O10. And this has the oxidation state of a +5. And both of these are used as ligands. So we'll talk more about what a ligand is when we come to the D block elements. We'll be discussing complex chemistry, and that's when ligands are involved. And then we've got the phosphorus halides, which are like the nitrogen ones, trihalides and trigonal pyramidal, but they're quite different. They're rather toxic. So PF3 is highly toxic. PCl3 is also pretty toxic. It's used as a pesticide. But also used to produce flame retardants. And this reacts vigorously with water to form phosphoric acid and HCl. However, it's quite different to NCl3, and this is because of electronegativity differences. So the polarity of bonds is almost flipped. So if we look at NCl, in this case, nitrogen is the more electronegative. So this actually has the delta minus. Whereas in a PCl bond, the phosphorus has a lower electronegativity than the chlorine. So this time it's the chlorine with the delta minus and the phosphorus with the delta plus. So this means the way it will react, these two things will react with a variety of reactants will be different because of what part is reacting with what part of the other reactant. And as this is the last video in the lecture 6 set of videos, here are some questions to try out, and in a couple of days I'll put the worked examples on YouTube.